Hello world, it's Craig. In the last video, which was part one of these two 8008 processor timing videos, I started with the full machine cycle, be it 1, 2, or 3 bytes long. And that machine cycle processes one full instruction, which is equivalent to, essentially a line in our assembly source file. For the 8008, it was called a machine cycle, but later processors, Intel, will rename this to be the more logical instruction cycle, and I'll occasionally use that term for the 8008 also. In this machine cycle, we expect the processor to take the instruction, decode it, process it, and get any additional bytes that are necessary, and then keep the program counter updated so that when the instruction is completed, the program counter is pointing to and it's all ready to fetch the next instruction. In the last video, I then broke those instructions down into subcycles and went into how an instruction can be a sequence of up to 3 of these 4 different types of subcycles, with the first one always being a PCI to fetch the instruction. And then if there's any more subcycles, they can either be a PCC for an IO, a PCW for memory write, but most commonly there'll be 1 or 2 PCRs for memory reads. And now in this video, we're going to break down the subcycle into the smaller individual configuration states called T-states, and that's what I mentioned in the last video. Depending on who, what, where, when, and how you learned about this, you may believe that the term T-state stands for timing state. Maybe you learned it as transition state, or maybe something else, or maybe the T no longer stands really for anything. And I'm not going to try to change your understanding of what T in T-state stands for. A T-state simply identifies a unique configuration of the processor in the machine cycle sequence. So you can think of a T-state as just being a snapshot of what's happening in that cycle. And interestingly enough, Intel didn't call these T-states in the MCS4 family. Even though that would have been what the commonly used name was in the computer industry in the time, for the 4004 and the 4040, Intel called these configuration states A, M, or X states for address, the machine instruction fetch, or execution subcycles. But of course, they quickly came back to the term T-state for the 8008. Now, we already had an inkling that these T-states existed in the last video because we know the 8008 is multiplexing its data bus like crazy, so something must be happening in a controlled sequence. It shows us that for each subcycle, there's at least 3, but there can be up to 5 T-states. And if a particular instruction doesn't need all 5 of those T-states within a subcycle, then the remaining states in that subcycle are abandoned and the processor just continues on with the next subcycle. Now, chances are that the next subcycle is just the PCI of a new machine cycle or instruction cycle. And if that's the case, the rest of the line in this process transition table is just grayed out or it's empty all the way across. But it also may be a continuation in the next subcycle of the same instruction, and these arrows show us the processor is just skipping ahead to the next subcycle. Also, in some cases, we can see that it takes all 5 states in that particular subcycle. The instruction is shown in this column, the subcycles across the top line, and those subcycles are divided into possible configuration states, called out as T1 through T5 for each of those subcycles. So each subcycle has a T1 to T5 available to it. And if we look at an individual cell in this table, that cell tells us what's happening during each of those T-states. As a reminder, a T-state is determined to be the period of the sync signal, and it extends from one rising edge transition of sync to the next rising edge of sync. So we can see from this diagram that this is one machine state. Now, during that sync period, the actual clock signals feeding the 8008 will have 8 edge transitions. There'll be 4 rising and 4 falling edges. So you can imagine that within the 8008, each of these transitions are making the little engine in the 8008 chug along with all of the tasks it needs to accomplish within that one T-state cell that we see in this diagram. However, for the most part, that's not something that we need to know unless we're designing hardware. And then, of course, we need to turn to the waveform diagrams to sequence our hardware's response to each of the processor's actions. But in this video, we aren't going to dig any deeper into processor timing than needed just to understand this IMM 882 CPU board. When it's preparing to fetch the next instruction to execute, the very first thing the processor does is to put out onto its data bus the low address byte of the program counter. And so that's so the glue logic then latch that byte onto the low address byte of the backplane. And this is the first of all the T states, so it's appropriately called T1. If we look at the first subcycle and down the T1 column, we can see that for all instructions, the T1 process is to put the PCL, which is the low byte of the program counter, onto the 8008 data bus. Now after it does that, it doesn't mention it here in the table, but the processor also increments the program counter low byte during this T1. And if this increment results in a carry, that carry bit is stored in a temporary register internally. After it finishes T1, the next thing the processor does is to put out the high 6 bits of the address and those 2 encoded subcycle bits. Remember the CC0 and the CC1 we discussed in the last video. And this byte is placed on the 8008 data bus so that it can be latched as the high address and the encoded subcycle bits onto the backplane. And that's what happens during T2. Our table shows us that for all PCI subcycles, the second T state is to put out PCH onto the bus so it can be latched. And again, it isn't mentioned here, but it'll be important later. In T2, the processor then takes any carry bit that was generated from the low program counter byte increment, and it adds it to the high program counter. So now the program counter contains the address of the next byte that's going to be accessed. So it's now at the end of T2, and the rest of the system can get to work because at this point, the system knows, in general, the type of subcycle, meaning if it's going to be an instruction fetch, a memory read, a memory write, or some kind of port I/O. And the address of that byte has been latched onto the system bus, so the subsystems can start decoding the address before the end of that T2 state. So far, we're still in the first PCI subcycle, so this is just a machine instruction fetch, of course. To the rest of the system, this instruction fetch is really no different than any other memory read, so everything is already all queued up. The memory card has hopefully decoded itself. It's selected the memory cell that has that specified memory address, and it's put that byte from that memory onto the data bus. And then likewise, in preparation to receive that opcode, the 8008 has its bus configured as inputs, and it's ready to enter T3 and latch that opcode. Just for a moment, we're going to take a little bit of a aside here, and we're going to look at a specific waveform timing diagram so that I can introduce the wait state. To orient ourselves with this diagram, with this waveform, here's the tail end of T1, and with this rising edge of sync. This middle part is going to be T2, and then T3 is going to start over here to the right with the next rising edge of sync. So where we left off at that end of T2, the address is out on the bus. The memory subsystem is then going to need to decode that address and select the correct chips, or maybe a bank of chips, and give those chips time to present the data to their outputs. Then the memory subsystem needs to gate that data byte onto the bus, and finally the 8008 needs to wait until all the transients have died off of the bus and that data is stable. And that can all happen fairly quickly, but most likely it's not going to be as quick as the processor is going from the end of T2, where it just finished putting up the address, to the beginning of T3, where it wants to latch in that specified data byte. So to take into account the relative speed of the processor and the memory, there's an input to the 8008 called ready. If this signal is asserted, the 8008 continues through the T states in the state transition diagram without any delay, and it goes right from the end of T2 into the start of T3 and latches in that data. But more likely, the memory subsystem is going to need extra time, so that memory is going to deassert the ready signal, meaning it is not ready, and that indicates to the 8008 that it needs to wait until the memory is ready. Now back to this waveform diagram, the bottom band of the timing diagram is this ready signal. And I don't want to dig too deeply here, but just enough to point out that in the very last clock pulse of T2, so here where phi 22 pulses, the 8008 pulls that ready signal. If that ready is asserted by the time that phi 22 comes along, the processor enters T3. So meaning that whatever external circuit was ready, the processor just goes right into T3. Now here phi 11 will be the first clock pulse of T3, and the processor is expecting the data to be placed on the bus by the falling edge of phi 1, and the data to be ready to be latched into the processor on the first falling edge of phi 2. But if that ready is deasserted by the time phi 2 comes along in T2, then the processor will enter what's called a wait state. In a wait state, the processor will continue to perform any internal housekeeping tasks like refreshing dynamic memory registers and so forth, but there won't be any bus transfers. The only output from the processor will be the transitions in the sync signal. And this diagram shows one wait state, but as long as the memory subsystem deasserts that ready signal, the 8008 just waits and waits and waits. And how many wait states there are will depend on the relative speed of the processor and the memory. With a slow 8008, maybe no wait states are required with fast memory. But, and I'm talking specifically about the Intellect 8 here, the 8080 version of the Intellect 8 that had the same PROM and the same RAM boards as the 8008 version, but in the faster 8080 processor, that processor board would automatically insert 1 or 2 wait states depending on which memory was being used. So I guess I misspoke a little earlier when I said that the memory subsystem deasserted the ready signal. Actually, it's more general than that. I just mentioned that in the Mod 80 version of the Intellect, the CPU board would deassert its version of the ready. But actually anything in the system could deassert the ready and force in wait states. And this would include a port I/O system, for example, or some hardware used to single step the processor. Anybody could force the processor into a continual wait state. Now, if it was just coming from memory, hopefully eventually the data byte has been provided and stabilized on the bus. The ready line is reasserted, and the processor exits the wait state, and it continues into T3, where it's going to latch in the data. Here we're still in the PCI, or the instruction fetch, and the processor's ready to accept the data. In T3, that data is going to be presented to the 8008 through the multiplexers and the buffers, already mentioned a couple of times. Let's look at the details in the subcycle 1 T3 cell. It tells us that the 8008 is going to take that machine instruction and latch it into its internal instruction register. That's what the IR is. And also latch it into another internal register called little b. Now, little b is not its formal name, as you can probably imagine. I don't know what its formal name actually was. But little b is not the B scratchpad register, that we see over here. Little a and little b are these two internal temporary registers right here off the internal data bus. Now, both are directly connected to the internal data bus, so in this PCI T-state, the opcode is just latched into little b at the same time it was latched into the instruction register over here. So back to our transition table. So we established that for the PCI, the T-states T1 through T3 are the same for nearly every instruction. The exception is down here with the halt instruction. And I guess we might as well get it out of the way now while we're talking about the halt. But when the processor receives this halt instruction, it will stop all fetching and all processing of instructions. It's like a perpetual wait state where it still outputs the sync signal, but it doesn't do much more. Remember, to get out of a wait state, the external circuit just needed to reassert the ready signal, and the processor would continue with T3. But once the 8008 is given a halt instruction, it becomes stopped. The processor is no longer fetching instruction. It's no longer polling the ready signal. Other than continuing to cycle the sync signal and maintain whatever internal dynamic RAM there is, the 8008 is pretty much lifeless, and this T-state is called stopped. But we're going to presume the instruction was not a halt, so now at the end of T3, the 8008 needs to begin processing that opcode. Let's say this was a register increment, which is this sixth instruction from the top. Increment and decrement, for that matter, they're both a 1-byte instruction, and they're completed within just the PCI subcycle. So in this first subcycle, we can see that after the first subcycle, the PCI, the remaining cells are grayed out. So everything to complete the register increment or decrement needs to be completed within these 5 available T-states of the first subcycle. Now, to execute the increment instruction, the 8008 needs to prepare for the add, and we see in T4, it's just noted as an X, which is an idle state. But idle doesn't mean the processor is not doing something. We know it's refreshing registers and likely moving something internally. For example, maybe it's moving our accumulator over to the arithmetic logic unit for the add. X is just an execution state of sorts. And then our table says in the T5 the processor does the actual addition operation and sets the flags. And we can presume that there's likely other unnamed housekeeping tasks to finish this instruction. Now remember, the program counter was incremented way back in T1, so that at the end of T5, the processor is ready to enter the next PCI where it'll fetch and execute the next instruction. Looking at this table, I'm pretty sure we can generalize and say that the first 3 T states in any subcycle will always have byte transfers on the data bus, and the last 2 T states, T4 and T5, will never have external transfers and will either not exist or will always just be internal processing states where the processor is only performing these internal transfers. Let's go down here to the jumps. Let's take a conditional jump. A conditional jump is one that will jump if the condition is true and fall through if the condition is false. This third column tells us the total number of states required for the whole or the machine cycle. For the first subcycle, the PCI in a conditional jump only needs 3 T states. So like every PCI, it puts out the low address, it puts out the high address, and it gets the opcode in T3. There may, of course, be a wait state in there if the memory required it. At that point, it skips ahead to the next subcycle, and because of that, one would think that this conditional jump cannot make any more progress without more information. Now, we will sidebar on that in a minute as soon as we finish out this machine cycle, but I have another comment on that conditional jump. In the second subcycle of this conditional jump, it's going to be a PCR. It uses the first 3 T states to get the low part of the destination address, but then it skips the last 2 available T states and goes directly into T1 of the third subcycle. And here in the third subcycle, it will always do the first 3 T states to get the high byte of the destination address. And then the processor evaluates the condition to see if it needs to jump or if it needs to fall through. And here we have notes 11 and 12 in these cells. And these notes say that if the condition evaluated as true, the processor will use these last 2 T states in the last PCR subcycle to update the program counter. So if it was true, it will use these last 2 T states, update the program counter so that then the following instruction fetch will be from this destination address, this new destination address. But if the condition evaluated false, so the program is just going to fall through this jump, then the processor skips those remaining 2 T states. So the program counter is not updated with the destination address. And that means it's done with this instruction and it can skip ahead with the next instruction. If we go back to the third column, we can see now why this instruction will take either 9 or 11 T states depending if it evaluates false or true. Those extra 2 T states may be needed to move the destination address into the program counter if the jump condition is true. And the same type of thing is true for conditional calls, meaning the decision is made at the very end of the machine cycle whether it's going to update the program counter or not. Now, likewise, a conditional return will take either 3 or 5 T states depending on how it evaluates. Now for that sidebar. Let's go back to the very beginning of this conditional jump instruction. In the very first subcycle, the 8008s retrieve the machine instruction in T3 just like every other PCI. We know that the next 2 subcycles are going to be PCRs, so the 8008 can get the destination address of where it will jump if the condition is true. But right now, in T3 of this very first subcycle, the 8008 already knows which condition is going to be considered because it just received the machine instruction. I mean, it already has the test condition, say if it's going to be a jump of carry or a jump of 0 and so forth. And at this point in T3, it also has the state of the condition flags, which have been sitting there unchanged since before this instruction even started. You know, the condition flags were set by the last instruction or, any instruction before that. And I can't think of a reason why the 8008 couldn't have evaluated the condition right now in T3 or, T4 if it needed it, of this very first subcycle and determine if the jump is necessary. And if the condition was true, then the processor needs to go ahead and finish the jump by getting the destination address and finally setting the program counter to that destination address. But if this condition were false, all it would need to do would be a double increment to skip the program counter past the destination address so that the program counter was now pointing to the next instruction in memory. Then rather than this instruction taking 9 T states if false, that could have been reduced to only 3 or maybe 4 T states if it was false. Even on a call where it needs to push the PC onto the stack, it still could have finished within the 5 T-states of the original PCI subcycle. And it sure seems that Intel could have reduced all fall-through conditional calls and jumps to one subcycle and cut the instruction time in half if it examined the condition in T4 in the PCI rather than in T4 of the second PCR, which is in the third subcycle, or already 9 T-states into this instruction. But there must be a reason. They switched things up a bit, but in the 8080, the transition table specifically says it evaluates the condition in the 4th T-state of the first subcycle, but it still uses all of the T-states for that instruction. So I'm interested in hearing about your favorite processor. The Z80, for example, takes 10 T-states for all jumps, non-conditional, conditional, evaluating true or false. They're all 10 T-states. For relative jumps, there's a difference. It's 7 T-states if it's false and 12 if it's true or if it's unconditional. So I haven't done a search, but it'd be interesting to see what other processors do on this. But anyway, back for the 8008, unconditional jumps, calls, and returns take the same number of T-states as their conditional counterpart that evaluated true. So it has to do the full instruction if it's an unconditional jump or call. By now, you've no doubt figured out that knowing which T-state the processor is executing is as critical as knowing which subcycle the processor is executing. And the system knows the subcycle because of those cycle control bits, the CC0 and the CC1 that were tacked onto the top address and decoded in the cycle decoder, which was D10 that we showed in the last video. Remember, it's the one that had the 4 outputs of not PCI, not PCC, PCR, PCW, and so forth. Now, we spent the last several minutes looking at the state transition diagram, and we've hit nearly all of the possible processor states. There's T1 through T5 called out here, so that's 5. We talked about the wait state, that's 6, and then we also talked about the stop state, which is 7. And I guess the next question should be, how many different T-states can there be? And we can answer that after we look at how we know which T-state the processor is in. Unlike the 8080, which puts out an entire status byte on the data bus, the 8008 only had those 2 encoded cycle control or CC bits that were tacked onto the upper address that told us the subcycle. So the 8008 is more like the 8085 in that it has actual status output pins that the 8008 controls to indicate its internal status. On the 8008, there are 3 encoded state outputs called S0, S1, and S2. And we see them here on the Intellect 8, the IMM 882 board on the bottom of the 8008, pins 11, 12, and 13. And on this board, these 3 status bits are generated by the 8008 are inputs to D2, which is just another 3205, which is a 3 to 8 or 1 of 8 decoder, whichever term you prefer. Think of the 3205 as a predecessor to the 74L138 3 to 8 decoder. It's got 3 inputs, 3 enables, and 8 outputs, with at most one of the outputs going low at a time, as selected by A0, 1, and 2, and then enabled by the 3 enable inputs. So there's 3 state encoding signals, and that means that there are no more than 8 total processor states that can be specified. The state table looks like this. We've got our 8 states, and then we have the configuration of the 3 state bits. And as near as I can tell, these are actually in no particular order. There is no real least significant, most significant bit. They're not in order. We've already discussed T1 through T5. We also talked about the wait state. Stopped, as I already mentioned, its purpose and application are as obvious as the name would imply. And that leaves this last state to discuss, which is T1I, with the I representing that the processor state is associated with a processor interrupt. These T1 and T1I states are both fetch T-state, and they're mutually exclusive. So let me emphasize that. In the process transition table we've been looking at in the whole video, T1 states could have been a T1I state. As far as the instruction processing sequence is concerned, there's no difference. Whether the machine cycle, again the same as an instruction cycle, starts with a T1 or it starts with a T1I, the T-states will be executed exactly the same in either case, and that particular instruction is processed the same in either case. For each instruction, the very first T-state of the first subcycle will either be the T1 or the T1I, but to the instruction itself, it makes no difference. Now, where this does make a difference is where the processor gets this instruction and where it goes to get the next instruction. So let me back up and set the stage for a hardware interrupt. Let's say that you have a little piece of code and that code is working, but then you decide to, maybe just temporarily add a register increment instruction. Maybe you want to see how many times this piece of code gets executed. You pick your least favorite register and insert an INE instruction. But this increment is not really part of your core code. It's an extra instruction that you just put in for this quick test. You reassemble the code, re-download or reprogram the EEPROM, rerun the program, and now the program is cruising along. It hits this new temporary instruction, it increments the register, and then it continues on with the next line of what was the original code. Now, a hardware interrupt is a very similar process, but rather than insert the instruction and reassemble or re-download the binary and restart the program, that extra instruction is inserted into the code essentially on the fly without the program stopping. Now, to do this, the 8008 has an input pin called interrupt, and that helps to accomplish this task. With a hardware interrupt, while the program is running, as soon as this interrupt signal is asserted, at the first opportunity, the 8008 needs to execute this extra instruction. And when this interrupt signal is asserted during the first T state of the next instruction fetch, because the processor is already doing one instruction, so it waits until the next instruction fetch, the 8008 will indicate its status as a T1 interrupt rather than a regular T1 state. And that T1 interrupt is this T1I that we saw in the state table. Now, the difference between your increment instruction that you explicitly added to the existing code, which you then had to reassemble, re-download, and restart, and this hardware interrupt version is the source of where that increment instruction comes from. When you put the instruction in, it was located in memory just in sequence with all of the other instructions. But when the processor is in an interrupt cycle, it expects the instruction will come from someplace other than the existing code memory space. So it's really quite simple. If the hardware interrupt is not asserted, instruction and data fetches are from normal code space. If the hardware interrupt is asserted, instruction and data fetches are provided and sequenced by some other piece of hardware, and this external hardware is going to continue providing all byte fetches to the 8008 until that interrupt input signal is deasserted. Think of it, it's like a baby bird in the nest. When the parent comes back, the ugly little thing opens its beak and it wobbles its head back and forth, and the parent jams something into its mouth. The baby bird doesn't care where that food came from. It just takes it and processes it as baby birds will. The 8008 is pretty much the same thing. During a T3, it opens its little data bus and some circuit somewhere puts an instruction into the 8008's data bus. 8008 doesn't care where the byte came from. It just takes it and processes it as little 8008s do. So let's work through this hardware interrupt. The 8008 is going along, it's running your program, and at some point this hardware interrupt signal is asserted. The 8008 finishes the current instruction it's working on as normal. But now when it begins the next instruction, rather than indicating it's in a T1 of the PCI, it indicates it's in a T1I state. The idea is that some peripheral circuit will now be triggered by this T1I status, and when it comes to the T3 cycle, rather than normal memory, this peripheral circuit will jam a predetermined machine instruction onto the data bus. And that instruction will be latched by the 8008 and T3 and then process that instruction as normal. Now, presuming that when that next instruction fetch cycle comes around, the interrupt line is not asserted, the 8008 will just continue with whatever the next instruction was before this interrupt came along. So it'll just continue the program as normal. Now, just as a little aside, don't confuse these hardware interrupts with vectored interrupts in more advanced processors like the 8085. When that interrupt hardware signal is asserted, other than outputting the encoded T1I rather than the regular T1 on the 3 cycle status bits, the only thing that the 8008 does differently is that after putting the program counter out onto the bus, like it usually does, it will not increment the program counter. And that's it. All this hubbub about interrupts, and that's the only difference to the 8008. It just doesn't increment the program counter. And what that means is that when all of this interrupt business is completed, the program counter will be exactly the same as it was before the interrupt started. But that also means that the processor is no longer incrementing any pointer like the program counter that's advancing to the next memory location in code space. So any pointer advancement needs to be provided by whatever alternate peripheral circuit is providing instructions and data bytes to the hardware interrupt. So once we go into a hardware interrupt, the processor is no longer incrementing the program counter, so whatever is doing the hardware jamming of instructions also has to be incrementing its own program counter if there's more than one instruction. Normally, to make our life easier, this instruction that we jam onto the bus, we're going to jam on a 1-byte instruction that can be provided to the 8008 during just this one PCI T3, and then we're done with it. We don't have to provide any more data bytes like an address or anything like that. And usually this 1-byte instruction is going to be set in hardware, say with a jumper block or a dip switch or some other configuration method. So pick any 1-byte instruction and imagine how that would work in your program. So for example, let's say this interrupt comes from a mechanical device through an RS latch. And the instruction you jam into the processor is a register increment instruction, just like it was before. Maybe it's your same INE that we used in the software example a few minutes ago. So that hardware tick sets the RS latch, whose output asserts the interrupt line. The processor services this interrupt, gets the INE instruction from whatever circuit provides it, and increments register E to finish that instruction. Now say there was then some logic to reset the RS latch when the processor indicated that it was in this T1 state. Now the interrupt is over. The 8008 gets back to doing whatever it was by fetching the next instruction. So now you can see why it was important not to increment that program counter, as I mentioned before, during that T1I state, because when the interrupt is over, program counter needs to be pointing to whatever instruction the processor was about to execute before the interrupt came along. Now you can probably see that it starts to get more complicated quickly if you want to use something other than a 1-byte instruction. So now that I said that, it isn't quite correct. It's not the number of bytes that are in the instruction. It's how many subcycles, and even more specifically, it's what we have to do in that second subcycle. For example, in that second subcycle, if it's just an out instruction where our external circuit doesn't have to do anything, then that's just as easy as all the other single cycle instructions. But if it's an instruction that has 2 cycles, and in that second cycle, we have to give another data byte to the processor, then we have to manage how to feed the processor that data byte in the second subcycle, T3 state. Whatever the instruction is, the hardware that's providing those instruction bytes needs to take it to completion. So for example, if a jump instruction is jammed onto the bus during the interrupt, then the peripheral hardware must not only supply the jump machine instruction, but it must provide the low byte and then the high byte of the destination address in the next 2 PCRs. And this can be taken to any extreme, and you can jam the whole rest of the program onto the bus if it makes you happy. But of all the single byte instructions, the restart is probably most commonly used since it provides a clean way for the processor to formally mark its place, since restart pushes the program counter onto the stack, and then it allows the program to effectively call any other interrupt service routine that can be whatever length, and then easily return back to the next instruction that was going to be executed before the interrupt arrived. Again, note that the program counter that the restart instruction will push onto the stack is the correct address for the next instruction since PC was not incremented during the T1I. It's a minor detail, but the 8008 only needs to be interrupted once for each instruction cycle, and once the interrupt acknowledge is asserted, the peripheral hardware becomes responsible for the opcodes and any data bytes until the end of that instruction. And of course, force-fitting the 8008 into this little 18-pin dip means there isn't actually an interrupt acknowledge signal, or any acknowledge signals for that matter. The T1I processor state indication is functionally the interrupt acknowledge, so you need to decode that T1I if you're looking for an interrupt acknowledge signal. Now, speaking of force-fitting into this little package, that reminds me, I hung a challenge out there a while ago that I don't think anybody answered. And maybe it was just in the last video, but it sure seems like a long time ago. The challenge was, there's a pin missing on the 8008 that I think every other processor has. The question is, what pin is that? Or alternately, if I'm wrong and some other processor has it, tell me what other processors are missing the same pin. So I'll put that challenge out there again if anybody is interested in responding. To finish up the interrupt discussion, and I think I finished this thought earlier, but as far as the program counter incrementing is concerned, the reason we didn't need a special T2I cycle was since the low byte program counter increment was inhibited during the T1I cycle, the low byte carry will always be 0 when added to the high byte portion of the program counter. So during T2, that carry will be added, but if it was a T1I cycle, that carry is going to be 0. There was no need for a special T2, or for that matter, there's no need for any other special T states. T1I is the only exception of all the T states. Also, to finish up with this hardware, as far as the IMM882 board is concerned, these interrupt instructions come from the dedicated interrupt data bus. And during the T1I state, the glue logic will select these multiplexers to switch the data input from the memory bus over to this interrupt bus. So something somewhere else puts those instructions onto that bus, and I'm just going to leave it there for now. While we're looking at the schematic, let's look back at this processor state decoder one more time, since there's one more thing I wanted to finish up with. This question is, why does the 8008 CPU board for this Intellect 8 bother decoding T4 and T5 states? You know, sure, they exist, and it's a 3-to-8 decoder anyway. They're already there, but it actually uses T4. We can see in the rest of the glue logic. And after all, those two T states where the 8008 is just doing internal functions, and so nothing is really happening externally. Remember, most of the T4s were either idle, or they were execution states marked with an X, or they're just internal moves. Now, this is a very interesting little tidbit, so if you were about to tune out of this video, you should have done it earlier, because now you're going to want to stay to hear this part. We all know that the 8008 isn't exactly the fastest reader in its grade level, and as such, it has the microprocessor equivalent of, say, a tendency to move its lips when it's reading to itself or when it's working through a problem. What I mean by that is, as the 8008 does internal moves using the internal data bus, it also puts this data out onto the external data bus. And so we can just watch what's going on internally by looking at this external data bus. The designers did not isolate the external bus, which means that during T4 and T5, the 8008 external data bus has, in fact, the same data as an internal data bus that's connecting to all of these internal registers, like the instruction register, little a, little b, the scratch pad registers, and so forth. If the design was intentional or not, Intel pushed this as a diagnostic feature. As shown in T4, there's note 3 in our transition state table. It says, note 3 says, contents of the internal data bus at T4 and T5 is available at the data bus. This is designed for testing purposes only. So I guess it was, if you can't fix it, feature it. If we look at subcycle 1 in our transition table, columns T4 and T5, we can see the sorts of insight we get if we monitor those 8008 data pins during T4 and T5. If it's a register-to-register move, for example, during T4, we will see the source register ID as it's moved from the opcode into register little b. Here on a restart, we would see the little a and little b being moved to the program counter in T4 and T5. Now, knowing this, you can get more insight to the 8008, so have fun and knock yourself out watching these internal bus transfers. There is one notable thing that comes out into the internal bus during a port input instruction, and those are the condition flags. We can see in note 16, during T4 of the second subcycle, the content of the condition flip-flops are available on the external data bus. And they take advantage of this. You can see here in the IMM882 that the 8008 data bus is latched during T4 in this 3404 latch, and it's put onto the Intellect backplane. And this is the source of all of those T0 through T7 bits that we see on the backplane. And that data can be used by other cards in the system or, as in this case, for the front panel interface. I think that is it for the 8008 processor states. As usual, there's a lot of information here, but then again, there's a lot going on inside the 8008. And I hope this helps with any diagnostics or if any of you are designing with this processor. Now, I have two more videos for this IMM882 board. One is on the glue logic and the other one is on the data path. Now, speaking of the data path, I haven't had any takers on that other challenge I have out there, which was to explain why Intel designed in this exclusive OR gate as the output buffer on the 8008 data bus. I had expected that to be unusual enough for somebody to chime in with the reason. I suppose there may be more than one reason, and maybe the reason I have in mind isn't even the best one, but I thought it would have generated some interest. So if you want to look at that and you have a reason why that buffer is an exclusive OR instead of any other chip they could have used, let me know or send me an email. Now, the last thing before we go, the channel has ticked over the 1,000 subscriber mark. So I wanted to give a special thanks to all subscribers, since that puts this channel into the top, what I think they say 8.8% of YouTube channels. And that's along with 1.1 million other channels that have at least 1,000 subscribers. But still, that's quite a milestone. In all seriousness, I really appreciate the encouragement to continue providing content. So that's it for this video. As always, this channel is entirely fueled by likes, shares, and engaging comments. I will talk with you later. Bye-bye.